Thanks everyone for joining us. I'm Ankit. I'm an engineer at LinkedIn in the AI platforms team, and I have Frank, my colleague, with me, who's the manager in the same team. In this talk, we'll give an overview of our training platform and our training clusters. We'll also talk about what are disruptions and what different kind of disruptions we see in our cluster. And then we'll dive into different strategies we use to handle these disruptions for our large language jobs. And we'll discuss other optimizations we do in our cluster to reduce the impact of these disruptions on the jobs. Finally, we'll share some tangible results that we have seen and the impact from all the improvements we have made. So LinkedIn is on-prem, so we have multiple regions, and these regions have heterogeneous capacity of GPUs and CPUs, different numbers, different SKUs, and we are able to dynamically route our jobs based on data and resource availability. So our platform runs over 1 million execution of tasks per month. This is a high-level diagram of our training stack. So at the very bottom, we have fleet management or cluster management, which is responsible for managing our GPU resources, different kind of networking technologies. And then we have in-cluster scheduling, where we do multiple optimizations to effectively utilize our GPUs and effectively allocate resources to the jobs. And then we have quota management, where we support hierarchical quotas for different verticals like ads, feeds, talent marketplace, to ensure fair resource usage. And then we also deploy multiple operators to orchestrate different kind of training jobs, depending on what users are trying to run. Some of these are open source, some of these are custom in-house operators. And then we have multi-region scheduler at the very top, which routes the jobs depending on data and compute availability to different regions. Observability is very well integrated throughout our stack, and each of these components in some way is aware of disruptions happening in the cluster, and they participate in us effectively handling them. So let's take a look at what a job lifecycle looks like in our cluster. So Flight is the primary orchestrator and user interface for our users. This is what they use to author their training workflows, which effectively, when user requests, let's say a TensorFlow job, it effectively creates a TF job resource type in a cluster. So as I mentioned earlier, we run multiple operators to orchestrate these jobs. These jobs, in turn, create pods, and we have our webhooks, which mutate these pods to add things like ability to fetch delegation tokens. We add init containers, or we annotate the pods to do quota management or provision storage. Similarly, we have our in-house scheduling plugins, where we do a lot of intelligent scheduling to properly utilize resources, and we'll talk some of those techniques later in the session. And we have controllers and servers to provide both metadata persistence, observability, and they also assist in checkpointing on demand. We'll discuss that later in the session. So what are disruptions? We define disruptions as an event where a running job needs to be forcefully killed. And this is usually due to the factors outside of job's control. When triggered, the implication of a disruption is basically the node gets drained. The draining time itself depends on the urgency of the disruption. So it could be immediately, or it could be at a scheduled time. We'll look at what kind of disruptions we see in the next slide. Disruption events can originate from multiple systems. So we have fleet management system who's trying to regularly update software. So they schedule these events. And as a ML platform team, we need to make sure the impact on jobs is minimal. So we have different kinds of disruptions in our cluster. The first is planned maintenance. So this is regular OS fleet upgrades, where we upgrade OS, security patches, or kernel upgrades. This typically happens at a bi-weekly cadence. So bi-weekly, we upgrade our whole fleet. And then we have unplanned maintenance. This is typically due to health check failures. So for example, if you're running a node with 8 GPUs, one of them could be unhealthy because of ECC errors, where we need to restart the node to reset the GPU state. But the node is still kind of functional. The jobs could still be running on them. So this category is basically the node is functional but running in a degraded state. So in this case, we do want to do maintenance on this node. And then the third category is we have preemption, where high priority job may need to preempt lower priority jobs. And this also causes disruption. So the common theme in all these is we have a very standardized process to create disruptions and to handle those disruptions. And we'll talk about that process. So in order to effectively handle disruptions in our platform, we have certain requirements from our jobs. And in turn, we provide them certain SLAs. So all jobs must be disruption ready. That is, they need to support checkpoint and restore. Additionally, they need to be able to handle restarts seamlessly. Like they shouldn't rely on hard-coded paths where a restart could effectively end up deleting certain things. Similarly, our platform provides SLAs where we allow maximum uninterrupted runtime of 24 hours. So our high-priority jobs can run for 24 hours without being interrupted for planned maintenance. During disruptions, we also ensure that jobs will get notification and time to checkpoint before they are killed. And at any point in time, not more than 10% of our cluster is unhealthy. If we go beyond that, then we open an incident and address it. So as a platform team, we also provide the libraries for our jobs to checkpoint. It's basically users just need to include the callback as shown in the code block in their trainers. For standard, if users are using standard data loading libraries that our platform provides, we also do data loader, checkpointing, and modal checkpointing. And we support multiple frameworks like TensorFlow, PyTorch. And we also have a very well-defined protocol. So if users are using custom trainer loops, they can implement their own checkpoint and restore mechanism. Users can also configure their disruption status, whether they're disruption ready or not. If they declare themselves as disruption ready, we can give them access to opportunistic capacity like spot instances. And similarly, they can define like maximum duration the checkpoint is supposed to take so that we can handle cases where the job is just stuck. It's not doing checkpointing. So our library also supports hierarchical checkpoints where for large language models, the checkpoint themselves can be pretty large and can take significant amount of time. So we have this hierarchical checkpoint where the primary checkpoint gets written to the in-memory local storage, and the secondary checkpoint is uploaded to the remote storage asynchronously. One thing to note here is this is, for example, in case of FSTP, where a model is sharded across nodes, all the workers need to take the checkpoint in parallel. So even if one worker gets disrupted on a node, it's not just that worker on that node that needs to checkpoint. All the workers in the training job needs to checkpoint simultaneously. So just before looking into what happens at a node itself, these are certain of job characteristics that we see. So single job can have multiple GPU, CPU workers, often part of a gang. And as I mentioned, disruption on a single node can basically disrupt the whole job. And each worker needs to checkpoint at the same time to ensure the consistency of the checkpoint. So let's take a look at what happens on the node itself when there is a maintenance event. This is the general life cycle or general set of events that Kubernetes pod goes through during an eviction process. So we have a maintenance service. Let's say it needs to do maintenance. It will set a disruption event. Our platform controller looks at that event, and it basically adds annotation to all the jobs running on that node. All the pods on the node and the corresponding jobs, it will add that annotation. It will also create a file called at a well-known location to indicate that the job needs to checkpoint. Then our maintenance service triggers the eviction workflow. It basically evicts the pod. At this point, our pre-stop hooks also detects that there is a file that indicates that we need to checkpoint, and it simply sleeps. It sleeps to prevent the kubelet from sending the SIG term to the main process, like the main training process. And then our checkpoint library in its callback also detects this file. So our checkpoint library basically triggers this code at a step boundary where the training loop has ended and we're about to start the next step. And at this point, it will do an all reduce to notify all the workers, since not just the worker that's getting disrupted need to checkpoint, it's all the workers that need to checkpoint. And this is done through a shared tensor where during the initialization of our training job, we have a shared checkpoint tensor, which is initialized to 0. And as part of this all reduce, the worker that gets the disruption basically sets this tensor to 1 and shares it with all the other workers in the job. Once all the workers see this condition being true, they all checkpoint. And when the checkpoint finishes, the checkpoint library exits with the non-zero code. And this basically causes the job to fail, but after the checkpoint. So this is like on-demand checkpoint. This can happen when we are about to do disruption. One thing to note is the termination grace period second is basically the maximum timeout that user configured for the checkpoint. So if in any part of this process, the process gets stuck, we will kill the job after this configured time period. So this is what an end-to-end lifecycle looks like. So we have a user launching jobs through flight. The job get orchestrated into multiple workers. We have a maintenance service that wants to do a disruption or maintenance. It creates a disruption event. Then our controller basically triggers a checkpointing, and it properly annotates the job to indicate that the job was disrupted due to maintenance event. And then our flight basically does a system level restart. What this means is users don't need to configure any retries. Our system will automatically retry in case of disrupted jobs. This is what the user interface looks like to users, where they clearly see the reason that the job was disrupted, and we made the second attempt to run the job. Now I'll hand the mic off to my colleague Frank, who will talk about how do we further reduce the impact on our jobs.
Yeah, thank you, Ankit. Yeah, I'll do a little bit deep dive into how we can further reduce the impact when we face a maintenance operation or unplanned disruptions for jobs specifically. But before we do that, I like to define some concepts. We have a bunch of nodes with different GPU SKU types, and each GPU SKU's group of nodes, we call them a node pool in a cluster. Each SKU have their own node pool. And all the nodes in the node pool are basically assigned one out of the 20 maintenance zones that we have. Each maintenance zones are determined by the physical fault domains. These could be data center power, network layouts, and etc. So in this diagram, you can see, for example, maintenance 0 will have a mixture of H100s, H200s, B200s, or even CPU nodes. But each maintenance zone, what we define is no more than or about 5% of the total capacity of the cluster. Now, knowing that, some of the challenges that we see is, for example, you can imagine a bunch of pods are scattered around across multiple maintenance zones. And in this example specifically, we have a maintenance operation going on for maintenance zone 1. Obviously, all the pods in that maintenance zone are going to be evicted. However, that is just not it, right? As Ankit mentioned earlier, a job could potentially span across multiple nodes, and all the other pods, for example, belonging to job A and job C are going to be disrupted, even though they belong to different maintenance zones. So the consequence is that even though we disrupted 5% of the entire cluster, there's potentially a lot more percentage of jobs that are going to be disrupted, 20, 30% or even more. So how do we solve that? We built a specific plugin called Maintenance Zone Aware Scheduling plugin in our scheduler. And what that does is exactly what it sounds like. By default, the jobs are spread across randomly in different maintenance zones. But with MZ-aware scheduling, our scheduler will prefer to pack these jobs onto the same maintenance zone. What that means is when we disrupt one maintenance zone, we're going to minimize the number of jobs that are going to be disrupted. A second challenge that we see with maintenance overall is repeated disruption for one specific job. This is extremely bad for long-running jobs that can span across multiple days, distributed training jobs, for example. In this diagram, for example, job 1 is running at T1. It receives a no quarter and drain event. The job will start to do some checkpointing. It will terminate. Then hopefully it will find a different node and to get the job to continue run, right? And then you'll go through the whole restore running. And at T2, it could very likely that node will be triggered a disruption event, and the job needs to do the whole thing again and again. For long-running job, it's especially susceptible to being interrupted multiple times. So what we do, as Ankit mentioned earlier, is we want to give jobs a minimum number of hours that I can do meaningful work, and that is 24 hours as we defined it. And for that, we also do node early notification, give advanced notification of 24 hours to the node as well. So at T minus 24 hours, we start the coordinating on the node. The node can run for at least 24 hours after that. It does checkpoint and then terminate. And since we do 2 maintenance zones every day, we're able to do the entire 20 maintenance zones in one cluster in about 10 days. To further optimize, we talked about it from the jobs perspective. To further optimize from the node perspective, when we do the draining of the node, it is likely that all the jobs and all the pods on the node are already done. So we don't need to wait for the whole 24-hour period. That's why we developed an early approval mechanism, such that as soon as the node is fully drained, when there's no active jobs running on it, we'll approve it, send the job to maintenance, so that it can come back healthy sooner. That ties to part as no more than 10% of our cluster is unhealthy, but we don't want the 10% to be unhealthy for the whole 24 hours, right? So when they become available, they should be able to join back earlier. And naturally, a third challenge is, from the jobs perspective, it can run into starvation. So our training cluster is usually very busy. There is almost always a queue of jobs waiting. And to add on to that, if you disrupt a running job, for example, this job would go all the way to the back of the queue. So it has to go through all this waiting again, get assigned a new node, and so on and so forth. Again, this is especially bad during the maintenance time because you're looking at 10% less of the overall cluster capacity. So wait time could even be more. So in order to solve that, the natural thing to do is we want to push disrupted job to the front of the queue. And within our training stack, we already have something called priorities defined. So there are high, medium, and low priorities, and higher priority jobs can preempt lower priority jobs. But we do not actually want to bump the job to the higher priority in order to push them to the front of the queue, because those jobs will also be able to preempt other jobs. So there is this vicious cycle you can imagine that I'm disrupting something. Now my priority is bumped. It's going to the top of the queue, and that disrupted job is in turn disrupting other jobs, right? And soon enough, when you do one cycle, maybe all the jobs in your cluster are disrupted. So we want to prevent that, and we introduced 3 new layers on top of the high, medium, and low. There are specific layers of priorities for disruption only, and those layers will not preempt any other jobs. They just bump the job to the front of the queue. So from our testing, our average queue wait time has reduced by 38% by those restarted jobs compared to not using this priority bump. And this is also a little bit different than the other 2 challenges that we talk about, which only applies to plant maintenance. For plant maintenance, we can do something about it, but for this specifically, it also applies to unplanned maintenance. When the job got killed, any jobs, right, can get bumped back to the top of the queue. And as Ankit mentioned earlier, there are also other type of failures. Overall, in the training, we've observed that the GPUs are generally encounter a lot more failures than our CPU nodes. About 7 to 10% of nodes will run into some type of failure every month. And there are instances where an entire node can just go down without any early warnings, right? And all the jobs on those node of 8 GPU cards will go down with them. So it is our recommendation, and it's generally a good option to enable periodic checkpointing so that the workloads don't lose any of those work that they were doing. So we talked about the how we do maintenance in one cluster, but what if you have multiple regions, right? So one thing that you can do is also stagger rollout of updates in different regions. Imagine this: at day 1, you roll out in region A. You start on day 1, go through the 20 maintenance zones, and finish on day 10. And for region B, you can start on day 2 and finish on day 11. And the benefit of that is you have 1 day of baking time across each region so that you're not rolling out all of your changes all at once. So at LinkedIn, we update our entire training fleet of thousands of nodes and across multiple regions, and we do that every 2 weeks. And what we observed is when we apply the three optimizations that we do, less than 1% of the total jobs are actually going to be disrupted. There's also fully automated remediation pipeline that we do that captures some of those health check issues, such as ECC errors and others. And they will go through the same disruptive pipeline, but these are also considered unplanned. So as a next step, something we're thinking of doing is not just simply reducing the number of jobs that are disrupted. And how about let's not disrupt the jobs at all? So elastic training come to our mind, and this is especially good that we don't need to redo the checkpoint and restore and reline up in the queue and all those stuff. When part of the nodes that landing out, when part of the pods that land in one MZ goes down, we can simply reduce the number of workers, and then when the node, without pausing, right, the training process, it will be training slower, but it will still be making progress and holding its pace in queue. And it can automatically go back up in terms of number of workers for that training job as soon as the nodes come back and become available. So that is something that we're exploring right now. And yeah, this concludes our presentation. Thank you so much for attending. I'll take questions. Thank you.
Hello, thank you for the talk. Thank you for sharing the insights. I had a couple of questions. In your maintenance operation, did you mention, are you giving advance notice for the whole zone at a time and cordoning it off, or some percentage of the zone? And how are you managing the extra capacity for that?
Yeah, so we have certain buffer in our capacity, and we do advance notice for the whole MC. But as Frank mentioned, like a lot of times if the job's finished, we immediately start maintenance process. So that reduces the idle resources, like that reduces the amount of GPUs that are idle. We also have the ability to schedule spot instances on those nodes. So let's say there are 8 GPUs, only 4 are running a job. We can schedule spot instances on those nodes so that we are not wasting capacity while the node is not being maintained.
Got it. I have 2 more questions. How do you set expectations and SLOs with the customers who may be submitting the jobs? How do you establish that contract?
Yeah, it's a hard problem. I think we went through a lot of, we worked with our bigger customers to enable checkpointing and restore with them. And the 24-hour SLA is a reasonable SLA, I think, to argue against, because their jobs can still fail because we can't control hardware failures or other unplanned failures. So that's sort of our contract, like that helped, like 24-hour SLA for high priority jobs helped appease like the customers' major concerns.
Got it. And one last question I had is, while submitting the jobs, let's say you are starting from scratch, you don't have any checkpointing system at all, how would you go about integrating and implementing the checkpoints and utilizing the system that you just talked about?
I'm sorry, I didn't get the first part of the...
The first part is, if you are starting from scratch today and there are no checkpoints in the jobs as of today, how do you go about integrating and implementing the checkpoints in the jobs and leveraging the system you described?
So we do provide, like for major frameworks like PyTorch, TensorFlow, and we have a very well-defined protocol that this is what you need to enable checkpointing. Beyond that, like we do have the ability where we can rule out certain jobs to be killed, but they need like approvals from multiple layers of management to justify why they cannot enable checkpointing. But our system does provide ability for us to list certain applications or jobs that they should not be interrupted. Like right now, I don't think we have like any job in that allow list, like maybe 1 or 2 jobs that were critical, but that's a very hard thing to get into.
And once you are doing the maintenance and you have cordoned some percentage of the nodes you mentioned, you are doing early checking to unlock the capacity. What system are you using to check it? Is it a custom kube controller or?
Yeah. So we have a custom controller that's just looking at the pods running on the node that's under maintenance and yeah, whenever
Got
the
it.
jobs finish on that node, it approves the disruptions.
Got it. Thank you so much.
Yeah.
Hey, hi. Thanks for the talk. My question is just an extension to the Ketan's question. So let's say application doesn't have checkpointing. How are you enforcing all applications who are coming in to train their ML models on your GPU platform? How are you enforcing to use the library, or how are you enforcing to enable checkpointing on all applications?
Yeah, so I think a lot of applications actually don't run into disruptions because as Frank shared the data, like we have 1% jobs that actually get disrupted. So some users are okay with those odds as well. Like if they're experimenting, worst case, their job gets killed and they rerun it. That's like the worst case scenario. But any user doing long running training, for them, like it makes sense to just add the checkpoint and restore.
Yeah, part of our SLA is also 24-hour guarantee that you won't run into planned maintenance. So user has that. If your job is running less than 24 hours and you're okay with hardware failures at that rate, then they're okay. And also, I think most of our implementations, we also write trainers for PyTorch, TensorFlow, any of those popular frameworks. So for those users, it's a simple migration to automatically get onboarded to our disruption readiness or checkpointing library.
Have you ever faced any situation like one long running job is running on a GPU node where we have a high priority job came, you had to preempt that existing job? So how are you handling those situations?
Yeah, I think that's a normal disruption scenario. Like
so you cannot give that much maintenance notice, right? So it's an urgent case. You have to preempt the other one. So because the new job is having high priority.
Yes. So the SLA applies to high priority jobs of 24 hours. But again, even high priority jobs are not that many in our cluster. You have to justify why it's okay for this job to kill other jobs.
Okay, thank you.
Yeah, thanks for the talk. A couple of questions. So one, you mentioned maintenance-aware scheduler. So can you expand on it a bit? Does it use stains tolerations or your own custom protocol to basically know which pod gets scheduled, like which node is coming up for maintenance, right? Yeah.
Yeah, so for the scheduler part, we use the Volcano scheduler, and it is easy to write external plugins for that, right? So essentially, we rely on the labels on those schedulers to determine what nodes are in what maintenance zones, and we club them together, club the GAN jobs together into the same maintenance zone as much as possible. Yeah.
That makes sense. For the maintenance itself, is your capacity hybrid? What I meant is it homogeneous or is it split across cloud providers? Like, how do you control maintenance, right? Like certain cloud providers release control plane versions at their own cadence, and I'm just trying to see how this interplays.
Yeah, we're completely on-prem, so yeah, we're in full control of the maintenance and which ones to do when. Yeah.
Okay, yeah. Thanks.
Yeah, good talk. Thought it was very informative. Did you consider any other alternatives to like the maintenance zone concept? Like, did you like anything like rolling, like keeping track of like let's say last maintenance time, and then having your scheduler be aware of that, and like packing together workloads, according to like nearest maintenance time or something like that?
Yeah, that's a good question. Today we don't do that, where we don't consider like the last time the node, like the maintenance zone was maintained. We don't have that intelligence because it's pretty dynamic. Like all the MZs are getting. So we already have a lot of constraints in our scheduler. So for example, we are fighting bin packing against MZ-aware scheduling. Then we have like network-aware scheduling as well, where we have multiple networks and we're trying to pack nodes within that network. So our scheduler is pretty complex right now, and this is a thing that we haven't needed so far. Like as we shared, only 1% of nodes are actually getting disrupted, so it's not a burning thing that we need to solve right away.
That makes sense. Second question, just curious, was I understanding correctly that your maintenance controller goes in and drops a file into the pod that then triggers the checkpointing, and then you have a pre-stop hook that kind of postpones the sig term? Why do that as opposed to just having like your pre-stop hook do that work, or just having your application handle the SIG term itself?
Yeah, so SIG term handling in training jobs can be a little bit tricky, because if, let's say, you are doing a training loop and you are in a all reduced process and you send a SIG term, the trainer, the other workers can fail, like if this process gets interrupted. And we also wanted to keep it simple for our users to also being able to implement like custom checkpointing protocols. So that's a very good question. Like we started with that, but it kept becoming more complex. And our thinking was that it might be more difficult for users in future to implement custom checkpointing solutions. This is very simple for users to understand. File shows up, you basically checkpoint.
And is it the pre-stop hook that generates the file, or is it a controller that execs in and then drops the file in there?
Yeah, it's our controller that execs in and drops the file.
Is that because every time you're stopping, you might not want a checkpoint, so you kind of want to have that option?
Exactly, yeah. Gotcha. Sometimes users just terminate from the UI and they maybe don't want a checkpoint, so.
Okay, thank you very much.
Yeah.
I have a question around so you mentioned you use this for node patching and stuff. What about Kubernetes upgrades or operator CRD upgrades? Do you have a separate cluster that you test that on? And what about if you have just two separate clusters and you just flip workloads over?
I think in an ideal world, if we have enough capacity, that we could do that. But today, Kubernetes upgrades or kubelet upgrades, they all follow the same process of maintenance that we shared.
Okay. And what if a job, relies on a deprecated API and stuff?
So your question is, what if
you would it's kind of how do you upgrade your clusters now? But right, I see.
Yeah, we monitor API server for deprecated API usage.
Yep. Fair enough. Okay, cool. Thanks.
Okay, thank you.
I think you mentioned that you run on-prem, not on Azure. Is that the case, or?
Yes.
So you use your own.
Uh-huh.
You use your own custom Kubernetes, or use managed?
I think we can
Yeah.
chat offline as well.
I think the question is whether we use managed Kubernetes or we deploy our own Kubernetes clusters. And we have some folks from our compute infra team as well who can better answer those questions.
So when you do the loading maintenance update, during the job run, would you run into the situation that because of the firmware update, all those things changed, right? Then multiple different nodes for the same job become inconsistent. Would you run into issues for the same training job?
So those kind of changes are rolled out very closely working with users, okay. So I think one example is maybe driver, right? We are upgrading NVIDIA driver and the CUDA is not compatible. So our platform team, first of all, makes sure that such kind of changes are not introduced in the cluster. And if we have to roll such changes, then we sort of code on the nodes in advance so that no jobs are running before we do maintenance on them. It's a more complicated upgrade than other upgrades, but there are very rare instances where we introduce such updates where the jobs just don't work on different versions. We have very little host dependencies. Driver is the only dependency that we have from the host.
Okay. How about the Kubernetes version? Do you also do that?
Do you mean we upgrade the Kubernetes? Yeah, I think that it goes through the same process. So we maintain kubelet and Kubernetes version compatibility.
Okay. Thank you.
Yeah, thank you.